Hello, here we are again with yet another review. Today it's going to be this book by Tom Chivers, Everything is Predictable, How Bayes' Remarkable Theorem Explains the World. So let's start very briefly with some information about the author. So Tom Chivers is a science journalist. He has received different prizes, including one by the Royal Statistical Society, I think, for science divulgation. And this is his third book. He has a previous one that I also have, which is this one, The Rationalist's Guide to the Galaxy, that explains very well the beliefs of the Bay Area rationalist, Bay Area centered rationalist community about artificial intelligence, about using Bayes' theorem for optimal decision making, about employing reason and evidence and so on for making decisions. This book is not completely disconnected from the other one. It centers on what most rationalists consider their core belief, which is Bayes' theorem and its implementation in how to make optimal decisions as a rational agent. He has other books about data. His other book, which I haven't read, is How to Read Numbers. And so, what is this book about? This is a pop math book, and it's meant to be an easy entry to understanding Bayes' theorem, and especially even more than just engaging in the pure mathematical formulations and aspects of Bayes' theorem, to the applications and uses of Bayes' theorem in different areas of knowledge, in personal life, in science, in the world, and how we understand how brains work, and so on. A couple of notes about style first. Tom Chivers is a very good writer, very entertaining. He has, sometimes some very funny, well-written asides to really connect with the audience. His style is pretty clear, transparent. I mostly understood everything in this book, even though, I haven't taken any courses on statistics yet. The mathematics should not intimidate you. This book has only one mathematical formula, which is Bayes' theorem, and you will be able to follow most of the argument. There are a couple of places where, especially when he was explaining the historical development of probability, where one might get a little bit confused, but the mathematics is pretty simple in general, even if it's anti or counterintuitive at times. So it's a book about Bayes' theorem. Bayes' theorem was discovered in the 18th century by a priest, nonconformist priest, an amateur mathematician called Thomas Bayes. And basically, in page 16 of the introduction, you have the theorem. The probability, it's here on the right of the screen, I believe. Yeah. The probability of A given B is equal to the probability of B given A times the probability of A divided by the probability of B. So it's not very intimidating mathematical machinery. I mean, you don't have here integrals, sigma notation, unusual operations. This is just like multiplication and division, although with probabilities that you have to calculate or be given before you begin to do the calculation. So, Bayes' theorem. This book is going to explain Bayes' theorem in quite a lot of detail. So, in a nutshell, what does Bayes' theorem tell you? So, it's basically a way of guessing probabilities of something and of updating your probabilities of something. Yeah. So, if you want to know how likely something is, given the evidence that we have, you would use Bayes' theorem. There is this feedback loop between a prior that you have, that is a preconception, which is subjective on how likely something is. Well, sometimes it's subjective, other time, well, it's always subjective, but sometimes you can use evidence that you have collected or other information to elaborate this first guesstimate of something. Then you collect more information, you collect the evidence, and you use this evidence to update your prior and to create a new probability, which is the posterior. And what Bayes' theorem gives you is a mechanism of doing this systematically and I would say quite rationally, in a way that the updating is not just ruled by subjective implications of what you feel strongly about, etc. It gives you, how could I say, it gives you an algorithm on how to update from a certain prior to a certain posterior and how to keep applying the process in a reiterated way. Okay, so the book is divided into 5 chapters. First, it starts with an introduction that explains you some of the nuts and bolts about Bayesianism. The main idea of why Bayes' theorem is important is because, like probability, it's a branch of mathematics that helps us deal with uncertainty. The world is an uncertain place. We have to make guesses all the time, and the tools of probability are here to help us achieve that. And Bayes' theorem very specifically sometimes leads to calculating probabilities that are really counterintuitive. Typical example, he gives it here, are these medical examples of how likely you are to have a certain illness if you test positive. And if the test has like a very high sensitivity, for example. In the example here, you have a test which is 80% sensitive, which means it detects cancer correctly 80% of the time. And it's also 90% specific, which means if you don't have cancer 90% of the time, it will detect that you don't have cancer. And then you ask the question, if a person does this test and gets a positive, how likely are they to have cancer? The answer is not 80%. In fact, the answer is usually much, much, much lower. And well, the book will explain you with some extra data that you need to include, like the prior, how likely is, what is the probability of having cancer if you are the person who took this test, and some other information. But, you know, usually you get probabilities that are really low compared to what you would expect. So this walks you through, the introduction walks you through a few of these cases in which you can use Bayes' theorem in different areas and see that it's something that breaks common sense. Okay, the next chapter, chapter 1, from the Book of Common Prayer to the full Monte Carlo. This is basically, it's the longest chapter in the book. It's about 80 pages long. And it's basically a history of probability and statistics from the 17th century, when probability first appeared in calculating the results of games of chance, like by people like Cardano first, and then in 17th century France by the Chevalier de la Meilleraye and Fermat and Pascal. So the book, this chapter explains how probability appears, how it's calculated, how errors are made in this respect. It then moves, it jumps to the 18th century, to Thomas Bayes, to his personal life, biography, his discoveries, and it continues. Thomas Bayes' theorem was not given a lot of importance at the time of its discovery. The author was a bit like Fermat, but even more so an amateur. At this time, you didn't have mathematical publications and everything. So Bayes' theorem was published posthumously, and it didn't exert a lot of influence, even though it was known. Other mathematicians in the continent, especially the Bernoullis, developed probability more, and they became much more important. And they developed a type of probability which the author of the book calls direct probability, which is basically assuming X is true, assuming you have a theory and the theory is true, how likely is it that you will encounter a certain result? And this is basically Bernoulli's theorem. And Bernoulli, discovers through this theorem ways of calculating results. I'm trying to find here the specific chapter dedicated to Bernoulli. I'm not going to find it now. But anyway, Bernoulli steers probability and statistics in a path that is this of direct probability on, given some knowledge that you already have, what can you predict about any samples that you would make? So like in coin throwing, like if you know that a coin is fair, so that's the hypothesis of the theory, and you toss a coin 100 times, what results should you get? You can't predict them exactly, but you will be able to predict that 50% of the time you should get heads, 50% of the time you should get tails. And you should get a distribution that is around this one. And the more and more and more you coin flip, the closer and closer and closer the distribution of the sample maps the one that is behind it, the one of the theory, of the hypothesis. So with 1 million coins, about 500,000 will be heads, 500,000 will be tails. And with 1 billion coins, and so on and so forth, the higher the number, the closer you get. And Bernoulli is able to calculate, I think it's explained here. He also uses balls where you're picking black balls and white balls from a box and trying to guess, given a certain ratio in the box, what is likely to appear from the sample, how big of a sample you need to get within certain intervals of error of guessing the composition of the original box and the ratio of balls, of black and white balls inside. And this is explored by Bernoulli and Ars Conjectandi. This is direct probability. This is very important because Bayesianism is the opposite. Bayesianism is inverse probability. So what Bayesianism is usually asking is, given this data, what can we say about the likelihood of a model that explains this data? So using the data for evaluating the hypothesis. Whereas the method that Bernoulli follows and that statistics and probability will follow after that is the opposite. It's given this hypothesis, which we take to be true, what will the percentages or the frequencies that appear in the data tell us about the hypothesis, or how well will it match the hypothesis? Yeah. Anyway, so this book continues after the 18th century. It explains the 19th century, the development of modern probability with Galton and this other guy, Fisher. Yeah. And the modern probability is mostly of what the book explains as, what was it called? Frequentist statistics. So the idea in frequentist statistics is, so again, you have to apologize, I haven't studied statistics yet, but the main idea I got is like, it works like this. When you want to test, you have a hypothesis that you want to test. Yeah, for example, eating fatty foods produces obesity. Okay, how do you test the hypothesis? Well, what you do first is you formulate the null hypothesis, which is the hypothesis that these two elements, obesity and consumption of fast foods, are not correlated, not connected in any way. Okay, that is the null hypothesis. And what you want is not to prove it. What you want is to disprove it somehow. How do you do this? You want to prove? You don't prove the opposite, but you want to show that it's unlikely that this null hypothesis is true. So what do? What you do is you do some experiments, you take samples, and then you use statistical and probabilistic tools and basically p-values, normal distributions, different stuff. If you are able to show that the data you got is really, really unlikely to match the null hypothesis, specifically if the p-value is less than 0.05, so only once in 20 would you get results like you got if the null hypothesis was true, then you can reject the null hypothesis. This doesn't mean that the alternative hypothesis, which is the one you wanted to study to begin with, that is that obesity causes or is correlated with consumption of fatty foods, does not mean that gets proved somehow. It just, you see a statistically significant correlation between those two variables. And so you can say there's something going on there. So this is how frequentist statistics works. Frequentists really rejected Bayesianism, but Bayesianism never completely disappeared. And the book explains to you how it continued to be practiced, and there were conferences and so on. And there were incidents and episodes where Bayesianism proved very useful. And like the cracking of the Enigma machine, although the author doesn't talk too much about that. But like in the late 20th century with machine learning, Bayesianism has made a big comeback, and now it's become at least respected as much as frequentism, as a theory for explaining statistics and for using in statistics and probability. Okay, I'm going a bit slowly. Let me go a little faster for the remainder chapters, but this was the biggest. Chapter 2, Bayes in Science. So Bayes in Science, basically, more than checking how Bayes' theorem is applied in different sciences, explains or explores the limitations of frequentist statistics. It talks a lot about the replication crisis, which was a big crisis, especially in psychology, but generally in the social sciences, that took place in the 2000s, 2010s, especially 2011 onwards, when it was seen that a lot of scientific studies could not be replicated. That is, they were tried again, and the results didn't replicate. And part of the reason for this is that you have some pressures when using frequentist statistics to get results that are statistically significant, less than the 0.05 p-value that we mentioned. And there are some conscious or unconscious ways of hacking, of cheating, of forcing the data to give statistically significant results. Yeah, so the book explains some of those methods, p-hacking notably, and yeah, it explains. The book clearly takes one side. The book is an apology of Bayesian statistics. Still, does a pretty good job at being pretty balanced. So this chapter, as I said, explains some of the problems of frequentism. The one I mentioned, p-hacking, also Lindley's paradox, and a few other issues. The difficulty of finding priors, which is a common criticism that has been made to Bayesian statistics. And he gets other people. He gets frequentist statisticians interviewed and talks with them about the issue in the book. So he does try to make a balanced case, but obviously he believes Bayesian statistics are generally better than frequentist statistics. Okay, chapter 3, Bayesian decision theory, tries to explain that Bayesian theory is not just a mathematical tool to be employed in probability and statistics. You can also use it as a model for ideal, rational decision making when you want to optimize for, using the data and updating appropriately so that you can have a positive impact in the world. So this chapter starts explaining you some aspects of logic, how deductive logic, which is the one that Aristotle and your courses on mathematical logic will teach you, is okay, but it's very, very limited. It can explain very few things. So you need induction and other methods of decision making, for which you will end up using things like Bayes' theorem. So, well, it explains you, how to use also game theory, which was developed in the 20th century by von Neumann and a few other thinkers on how to make optimal decisions when there are different persons competing for different objectives, and what is the best way of maximizing utility, of getting the best results possible. And for this you use different mathematics, but you also use Bayes' theorem. Yeah? And well, this chapter also explains how you can get priors, how there are some tools that help you get better priors than just randomly distributing the probability of something. You can use multiple hypotheses, hyperpriors, and so on and so forth. Okay, the next chapter is Bayes in the world. Basically, what this chapter explores is how irrational humans are. So the previous chapter explained that a completely rational, expected value and utility maximizing individual generally uses consciously or unconsciously something like Bayes' theorem for making decisions. And this chapter explores the fact that humans are not optimal decision makers most of the time. We can be pretty irrational. There is a lot of literature on how irrational humans are when making decisions, how much they depart from a Bayesian rational thinker or from Homo economicus. And lots of studies, especially the book by Kahneman and Tversky, which I haven't read yet. It's here, Thinking Fast and Slow. This book is basically an explanation of, I haven't read it yet, but it's basically an explanation of two types of thinking that humans have, a more heuristic intuitive type and the more rational one. So are humans irrational? Well, the book explores this through the typical logical fallacies that humans fall over for. But the book ends up on a pretty optimistic tone, like saying, we are not as irrational as we think. We are mostly intuitively Bayesian, and when we are presented with concrete examples, we generally make the right choices. But sometimes, probability is not very intuitive, so sometimes we get it wrong. Also explains super forecasting, how there are some individuals that are very good at using something like intuitive Bayesianism for giving probabilities to events and updating them, and how they can get relatively good results at guessing different things that might happen. Yeah. Okay, next chapter, chapter 5 and last, there's a small conclusion at the end, is the Bayesian brain. And this is one of the more speculative chapters of the book. So it starts, it tries to explain that the way it starts with some of the typical tricks that our brains play of us, optical illusions and things like that. But basically what it develops, the thesis it develops, is that the whole way we perceive the world, that our senses perceive the world and interact with the world, is Bayesian. It's a feedback loop in which our mind has this prior, it gets information from the senses, and it uses that information for updating. And well, it makes a case which is moderately convincing, I would say. So, and then the book comes with a conclusion that just summarizes the key ideas of the book. Yeah. How Bayesianism is the best tool for updating and your information about the world, how the world is Bayesian, and how we can profit from using a Bayesian mind frame for searching for truths. Okay, 22 minutes of it. This is a bit long. I'll try to finish in 5 minutes. So, conclusions. I found the book very useful. As I said, I haven't taken a course on statistics or probability, although I've read some popular stuff, so I'm not complete ignoramus in those areas. I found the book very useful, both for getting a clearer picture of how Bayesian probability works, what it consists of, and it's also helped me get rid of some prejudices I had. I am not a person that likes uncertainty. I'm pretty risk averse, which means like the areas of mathematics I most tend to like are not probability and statistics, those that are useful for the world, but really about uncertainty. Now, from a very superficial knowledge of Bayesianism and frequentism, I had the intuition that I would be a frequentist. I would feel closer to the attitude in frequentism, which is more about assuming that the world is objectively a certain way, and then you test and try to confirm theories about that world. Whereas Bayesianism has this subjective flavor of starting with priors that can be wildly subjective and polishing them and updating them to get a correct solution. So this book has updated me. I'll do a Bayesian updating. So it has updated my priors, and my posterior is now much more favorable to Bayesianism, than to Bayesian statistics. As I said, this is a very readable book. You won't need complex mathematical knowledge to read it. It's a very entertaining book, very well written. Sometimes one feels that chapters could, especially some of the last ones, could be maybe a little bit better intertwined. They feel sometimes like a bit discreet in the topics they cover, but I think the author has done a really, really good job, and I can only recommend you this book. So give it a look. Everything is predictable. Tom Chivers.